What the? How did that just start? All right. Any questions? Okay. All right, moving on. Take a look at the next problem. We already did this problem, right? All right, next. So here, yeah, this is kind of tricky because you really have to see like where things are. Okay. All right. A particle of mass 2 kilograms moves along the x-axis through a region in which its potential energy U of x varies as shown in figure 8-41. When the particle is at x is equal to 2 meters, its velocity happens to be negative 2 meters per second. So it has kinetic energy definitely, right? At x equals 2 meters. A, what force acts on it at this position? So they want to know what's going on at 2 meters. So here is 2 meters right here. This is really hard because that's 2 meters. And where is that located? It looks like it's located at, I don't know, like 8. Like 2 meters. Like negative 8. All right, it's really hard to justify all this, but all right. And then, if we were to look at, so if we were to actually find the slope of this line, which looks pretty straight, I can find exactly how much force was acting at that position. Does that make sense? Right? So here at 2 meters, we can actually find the slope of this, or negative slope, I should say. So force is equal to negative du dx. Okay? So it's a negative of, well, let's see. If I were to look at this at 1, I don't know, that looks like 1, 2, 3. Is it like 3-ish, I guess? Like 2.8 or whatever. All right. And then if I look at here, that looks like 17.5-ish. Or maybe 17, right? Negative 17 at like 4 meters, right? So I would say if I use these 2 points and find the slope for these 2 points, you could probably figure out the slope of the rest of the whole thing, right? So you could say negative 17, right, minus negative, I don't know, like 3, right, 2.8 or whatever, right, like 2.8. It's a little less than negative 3, I guess, right? Divide that by, right, 4 minus 1. All right, is that good? So what is that, John? That looks like negative 17 plus 2.8. So that looks like right, 14.2, right? And negative of negative 14.2 over 3, right? I get like 4.7333 repeating, right? Newtons. It comes out positive because it's negative of negative. Is that okay? All right. So that's part A. And then at part B, they're asking, right, between what limit of x does the particle move, right? They want to know what is the maximum potential energy, basically. So for part B, we know at 2 meters, right? X equals 2 meters, right? We know the kinetic energy at x equals 2 meters, and that is 1/2 times 2 times negative 2 squared. And that is equal to 4 joules, right? Therefore, right, at x equals 2 meters, right, we have kinetic energy and potential energy at x equals 2 meters. And kinetic energy, we said it was 4 joules plus, what is the potential energy? Potential energy at I don't know, it's right here. I'm going to say 8, negative 8, right? So negative 8 joules. This is 4 joules. So is actually going to be at negative 4 joules, right? Is the total mechanical energy. So this is total energy. So this represents, right, total potential energy max, which is negative 4 joules, right? When kinetic energy is equal to 0. So it will be confined right here at negative 4. So the answer is slightly off from the, this is your max, which is at negative 4 joules. Okay? So what's going on at x equals 7? So at x equals 7, this is what's going on right here. When x is equal to 7, you have 17, negative 17 joules of potential energy. So for part C, at x equals 7 meters, your potential energy is negative 17. All right? So since total energy initial is equal to total energy final, total energy initial, you have negative 4 joules. Because that's the maximum potential energy we started with. This has to equal to kinetic energy at 7 meters plus the potential energy at 7 meters. So negative 4 is equal to, right, 1/2 mv squared at 7 meters plus, right, plus potential energy at 7 meters is negative 17. All right. So if you bring this to the other side, it becomes 13, right? is equal to 1/2 times 2 times v squared. So v is equal to square root of 13. And what is square root of 13? I guess 3.6 meters per second. Is that okay with everybody? Okay. This is a very important problem. All right, what's next? Here, conservation of energy. Looks like conservation of trees too, right? It is claimed that large trees can evaporate as much as 900 kilograms of water per day. A, evaporation takes place from the leaves. To get there, the water must be raised from the roots to the tree, right, and through the leaves. Assuming the average rise of the water to be around 9 meters from the ground, how much energy must be supplied per day to raise the water? So we have 900 kilograms of water. It has to be raised up. So this is the force, right? Force by the tree to the water, right? Tree to water, right? That force has to be the same amount as the water weight itself. That has to be FgH2O. So these have to be the same, basically. Okay? So we could say that this is equal to, right, FgH2O, and that is just mg, m of H2OG. And it has to be raised 9 meters. So this here, my delta y is equal to 9 meters. So notice the angle between my f and delta y, your theta is equal to 0 degrees. Are we okay with that? All right. So how much work is being done? Well, we know work is equal to F dot delta y. But in our case, it's F tree to water, right, dot delta y. So we know that this, we already said, is equal to mH2OG, right, times delta y times cosine of 0 degrees. So here it is 900 kilograms times 9.8 times 9.0 times 1. So the work done by tree is equal to, I think you get something like 79,380 joules of work is done by the tree to breathe for Earth. That's how they're doing a lot of work. Yeah? So go hug a tree today and say thank you. That's your homework. Well, at what rate is this energy supplied if evaporation is assumed to occur during 12 hours of day? So average of 12 hours of sunshine, that's when it happens, right? So for part B, they want to know the rate. And rate is power, is work divided by time. But the time they give us is actually 12 hours, but we can't really use hours because we have to use, right, MKS system. So 12 hours times 3,600 seconds per hour, right? So if you work that out, then you get 43,200 seconds per 12 hours. So that's the time we have to use, all right? So we already know what work is, right? 79,380 joules over 43,200 seconds. And that comes out to 1.84, what? Right? So 1.84 watts. So it's not too much power, but we have hundreds of millions, hopefully billions of trees doing that for our Earth, as long as we don't cut it down. All right? So go thank a tree and hug a tree today. All right? All right, next. No, it's just watts. It's joules per second. So this is, yeah, this is the rate of how many joules per second it is. Yeah. All right. Next. Well, we have 30-gram bullet initially traveling at 500 meters per second, penetrates. So first of all, we can't really use grams right here, right? So mass should be measured in kilograms, right? And it travels at 500 meters per second. This looks like the initial velocity, v, or initial speed, vi, and it penetrates 12 centimeters. This is how much the bullet penetrates into the wall, and that's the delta x. And that distance here should be measured in meters. So my delta x should be 0.12 meters. Okay. So before it stops, so my final velocity is 0. A, what is the reduction in the bullet's mechanical energy? Well, how much reduction do we have? It looks like there's definitely work done by friction. So work done by non-conservative force does not equal to 0. Therefore, we cannot use total energy initial is equal to total energy final. We have to use work done by non-conservative force is equal to, right, change in kinetic energy plus change in potential energy gravitation. No springs, so we're not going to even put the springs, change in potential energy springs down. But you can if you really want to, but it's going to be crossed out anyway, right? There's no potential energy in spring. And there's no potential energy gravitation change either because the height doesn't change, right? It starts at this height and finishes at that height, so no potential energy gravitation change, right? No height change, right? And here, no spring. So we only have to work with this change in kinetic energy. So work done by non-conservative force, or simply work done by friction in this case, is equal to kinetic energy final minus the kinetic energy initial. Final kinetic energy 0 because it comes to stop. And work done by friction we know as F friction dot delta x. Now friction is acting in this direction, and delta x is going in that direction, so the angle theta is equal to 180 degrees. Therefore, right, F friction times delta x times cosine of 180 is equal to negative 1/2 mv initial squared. So they just want to know what this is for part A. For part A, they want to know how much reduction of energy that we have. So if we work this out, we get negative 1/2 times mass 0.030 times 500 squared. And if you work it out, you're going to get negative 3,750 joules of energy. That negative means that's how much it was taken out of the system, right? So the reduction of the mechanical energy is equal to 3,750 joules. All right. So what about part B? They want to know, assume the force of the wall and the bullet is constant. All right, for part B, they want to know what the force is. So we know the force, friction, times delta x times cosine of 180 is equal to negative 3750. This is negative 1. This is 0.12, and we're solving for friction. So if you calculate for friction, you're going to get positive 31,250 newtons. So that's how much work was done by the wall. Well, this is how much force was applied by the wall to the bullet to stop that bullet from coming in at 500 meters per second. And it takes 0.12 meters to stop it. So if you ever have to design a bulletproof vest, you have to know what kind of bullet you're working with and how fast it travels before it gets hit. And all it has to do is just it has to absorb that much energy, right? All right, next, a bear. So 25 kilograms. This looks like a baby bear. 25 kilograms. It's a baby bear. Slides from rest. So we know the initial speed of bear is 0. Right? Slides down a lodgepole, pine tree. Okay, weird. Moving with speed of 5.6 meters per second just before, so V final happens to be 5.6 meters per second. What change occurs in the potential energy of the bear? So for part A, the change in potential energy for bear is just gravitation, really. There's no spring involved. So it is potential energy final minus the potential energy initial, right? Potential energy final for gravitation is 0 because the height is 0. So the only change in potential energy that we have is negative, right? mgh initial. Therefore, the change in potential energy happens to be negative 25 times 9.8 times 12. So the change in potential energy gravitation comes out to negative 2,940 joules. What about part B? Part B asks, what is the kinetic energy of the bear just before it hits the ground? So for part B, right, kinetic energy final is equal to just 1/2 mv final squared, which is 1/2 times 25 times Vf, which happens to be 5.6 squared. And if you work that out, you're going to get 392 joules. Then for part C, what is the average frictional force that acts on the bear? Well, average frictional force that acts on the bear. Work done by friction is equal to change in kinetic energy plus change in potential energy gravitation plus change in potential energy spring. We don't have any spring involved. We already know what this change in potential energy gravitation is. That is that. That's negative 2940. So work done by friction is equal to, right, force friction dot delta y. And that is equal to kinetic energy final minus the kinetic energy initial plus, we already know what that is. That is negative 2940. Well, we know kinetic energy final, we calculated to be 392. We know the initial kinetic energy is 0. So 392 minus 2940 is equal to F friction times delta y times cosine of 180. So we know cosine of 180 is negative 1, right? Therefore, F friction times delta y, which is 12 meters, times negative 1 is equal to negative 2548. So my frictional force comes out to, well, this negative and this negative will cancel out. Comes out to 212 newtons of force is applied to the bear by the pine tars on the tree. Okay? All right. All right, next. Here, you push a 2-kilogram block against the horizontal spring, compressing the spring by 15 centimeters. So this, you have to convert that into meters. So that is X for the spring is 0.15 meters. When you release the block, the spring forces it to slide across the tabletop. It stops at 75 centimeters from where it's released. So this is actually delta x. But this delta x looks like same thing as this x here, so I don't want to get confused. I'm going to call that just distance d that it travels. And this is actually 0.75 meters, not 75 meters. So I don't want to get confused between this delta x and this x of the spring. So I'm going to call that delta x d. All right. The spring constant is 200 newtons per meter. So we know the K value. The K is equal to 200 newtons per meter. What is the coefficient of friction? So this has friction here from all this. So we're going to consider this to be our position A, and this is our position B, initial, final. Okay? We know the work done by non-conservative force is not equal to 0. Therefore, we have to use work done by non-conservative forces equal to change in kinetic energy plus change in potential energy gravitation plus change in potential energy spring. We have to do that. So work done by friction is equal to change in kinetic energy plus change in potential energy of spring plus change in potential energy gravitation. Is there a change in potential energy gravitation for this table that's horizontal? No. No height, right? Change. So no height change. Well, it starts here when it's compressed Is it moving before you release it? No. After it travels here, it comes to a stop. Is it moving? No. Do we have kinetic energy at A? Do we have kinetic energy at B? So we have no change in kinetic energy. So the only thing we have to work with is the potential energy of the spring. So work done by friction now is equal to potential energy of spring final minus the potential energy of spring initial. Is there any spring acting on the block final when it's way over here? No, spring does not come into play at the final position, so this goes to 0. So now we have work done by friction, which is frictional force times D, I should say, D, not delta X. So I don't want that confused. D is equal to negative potential energy of spring initial. So here, frictional force is going to act this way, right? Frictional force is acting this way. And D is acting that way. Therefore, theta is equal to 180 degrees. So friction, which is mu times F normal times D times cosine of 180 is equal to negative 1/2 k x squared. Normal force, which is that way, is same as my mg. So my F normal is equal to mg. So mu times mg d times negative 1 is equal to negative 1/2 kx squared. Now let's plug and chug. Mu m2 g 9.8 d 0.75. Notice how negative here and this negative cancels out, is equal to 1/2 times 200 times 0.15 squared. You can solve for mu. So mu sub k comes out to 0.153. All right. Next. So here, a cookie jar is moving up a 40-degree incline at a point 1.5 feet from the bottom, so of the incline. So this is from here to here is 1.8. Oh my God, it's feet. Oh, how archaic. Be careful. They're giving us feet. It's British empirical system. Oh. So it's starting here, basically. So we can actually consider this to be our 0 if you want. Okay, so here is our 0. So my y is 0 at this location. Well, this will obviously have, right, fg going down this way, and fgy and fgx, and of course the normal force. And you know my F normal has to be same as FGY in this case. I'm not going to go through all of that again, right? You guys should know that. Which is equal to, this angle is 40, so FG cosine of 40 degrees, which is basically mg cosine of 40 degrees. What else do we know? Well, when it gets to the top, it's going to eventually come to a stop, right? So here's point A, here's point B. At this location, my V at B is equal to 0. Instantaneously, it's going to stop. So this distance here is my H final. So it gains potential energy. But there's definitely some friction going on, and the mu sub k is equal to 0.15. So there's work done by friction. All right, so part A, how much further up? So they want to know, what is this John right here? They want to know how much will this go up. They want to know what this delta x is. Okay? All right then, now that we know that, let's do it. So for part A, we're looking for delta x, the blue delta x right here. We know there's work done by friction. Therefore, it is change in kinetic energy plus change in potential energy, gravitation, plus change in potential energy, spring. There's no spring here whatsoever. So I'm going to just cross out that. Right? So here, work done by friction is F friction dot delta x. And that is equal to kinetic energy final minus the kinetic energy initial plus potential energy gravitation final minus the potential energy gravitation initial. We know initial potential energy is 0 because my y is 0 at this point, and I made that to be my 0. So this is my 0 potential energy initially. At final kinetic energy, when it reaches the top, the speed is 0 at the top, right? So I have no kinetic energy at the top. So I only have these two equaling that. So we know friction is equal to mu times F normal times delta x times cosine of delta x is this way, friction is that way, so cosine of 180, good, is equal to negative 1/2 mv initial squared plus mgh final. We know F normal is mg cosine 40. So mu times mg cosine of 40 times delta x times negative 1 is equal to, right, negative 1/2 times m times vi is 4.5 squared plus m times 32 feet per second squared times hf. Maybe I should have put that. Let's plug all the values in. All right, so 0.15, right, times m, which we don't know. I guess we could cancel out all the m's, huh? M's. So maybe we can just put 32 in here instead, right? So this is gone. 32 times cosine of 40, right, times negative 1, right, is equal to all this mess. So if you work it out, I think you're going to get negative 3.677 delta x is equal to, here you get negative 10.125 plus 20 point, wait a minute, something's not right. Yeah, we have to use this HF in terms of this delta x. So if I were to look at this, here is my delta x, here's my H final, here's my 40 degrees. So cosine of theta is equal to, or maybe I should say sine of theta is equal to, right, HF over delta x. So I can substitute, right, my HF as delta x sine of 40 degrees. Okay? So if you do that, right, so 32 times delta x sine of 40 degrees is what HF32 is. That comes out to, right, 20.57 delta x. So if you work it out, you're going to get 10.125 is equal to 24.25 delta x. So my delta x comes out to, I believe, something like 0.4176 feet. And if you multiply that by 12 inches per 1 foot, it comes out to 5 inches. Okay? All right. So what about part B? Part B asks, how fast will it be going when it slides back to the bottom? So when it slides back to the bottom, right, now my delta x is equal to this delta x plus this delta x, right? So this is 1.8 already, plus my delta x, which is 0.4176. So this delta x is actually 2.218 feet, right? That is 1.8 plus 0.4176. Okay? So that's my new delta x. The height, h, from here to here is simply, right, delta x times sine of 40, which is, right, 1.425. That's my new height. Okay? So 2.2 times sine of 40 is basically what that is. All right, then. The work done by friction now is equal to, so here's our new starting point, A, and here's my final position, B. So here, again, change in kinetic energy plus change in potential energy gravitation plus change in potential energy of spring. Again, spring we're not going to worry about. There's no spring here, right? So mu F normal delta x times cosine of 180 is equal to, right? We have kinetic energy final minus the kinetic energy initial plus potential energy gravitation final minus potential energy gravitation initial. Initially, kinetic energy is 0 because once it goes to the maximum height, it stops instantaneously before it comes back down. Potential energy final gravitation is 0 because now once it reaches the bottom, this is our new 0, so I have no potential energy gravitation whatsoever. Right? So these two are the only one remaining. We know F normal is mg cosine theta, right? So mu times mg cosine 40 degrees, right, times delta x times -1 is equal to, right, 1/2 times m VF squared is what we're looking for, right, minus m times 32 times height, which is 1.425. So my mass gets canceled out. Right? This whole thing right here is 32 times, so 0.15 times 32 times cosine of 40 times -1 times delta x is equal to, well, delta x we know what it is, right? It's, sorry, 2.218, right? 1/2 VF squared minus this mess, which is 45.6. This whole thing comes out to -8.156. Okay. If you solve for VF, your VF comes out to 8.66 feet per second. All right. Any questions? Yeah. Question. That's G. 32 feet per second squared. Right. Yeah, 32 is the acceleration due to gravity in feet per second squared. I guess I should have put like mgh here. All right. How are we doing so far? All right. All right, so here we have a small particle, right, sliding along a track with elevated ends. So here, it starts here, you release it, and it's going to slide down. But in the flat part of the length L, there's going to be some friction here. Here, frictionless. Here, frictionless. But here, there's definitely friction. So this thing's going to slide down, and then slow down, and maybe go up to maybe here. And then it's going to slide back down, and then it's going to go slow down, maybe get up to here. And then it's going to slide down, and then slow down, stop somewhere. We don't know where it's going to stop. All right. So we definitely know there's mu sub k happening at this part, which is 0.20. So initial is where we start, and eventually final is going to be somewhere here. It's not going to stop here, obviously, right? Or it's not going to stop here. It's going to have to stop somewhere along the flat part, right? So we're going to assume it's going to be somewhere along the flat part. So what does that mean? That means work done by friction has to equal to change in kinetic energy plus change in potential energy, gravitation. No spring involved. Well, if this is the initial and this is final, how much is it moving at point A? Good, like you said, nothing. It's not moving at all, right? Because it's released, right? So kinetic energy initial is 0. When it's stopped at the bottom, what's my kinetic energy? 0. So there's no change in kinetic energy at all. So work done by friction now is equal to, right, potential energy gravitation final minus the potential energy gravitation initial. What is the height at final position? 0. So how much potential energy gravitation do I have? Final position? 0. So we're going to consider this to be our 0. Therefore, work done by friction now is equal to mu times F normal times delta x times cosine of 180 is equal to negative mgh. Now, height, they said, was equal to L over 2. It's given to us right here. So we can replace that height with L over 2 eventually. So here, the normal force only is pertinent right here. It's important along the flat part. So in this flat part, your normal force is your Fg, right? So here it can be substituted with mg at this normal force along the flat part. Here, we don't have to worry about it because there's no friction. We only worry about the flat part when there is friction. So mu mg delta x times negative 1 is equal to negative mg L over 2. Well, look at this. M's cancel out, G's cancel out, negative 1's cancel out. What do we have? We have mu delta x, right, is equal to L over 2. So mu is equal to 0.20. Delta x is equal to L over 2. What's 120? 0.20? That is 1/5 of delta x is equal to L over 2. So my delta x is equal to 5L over 2, or 2.5 L. So what's going to happen? This thing's going to go down and then come up this side. So it traveled 1L. And it's going to come back down, travel through, and come to here. That's 2L. And then it's going to come down and then slow down, stop right at half L. Therefore, it'll stop right in the middle. Okay? Boom. All right. Any questions? How much time do I have left? All right. I guess this is the last problem. Okay. And oh, great, perfect. All right, let's take a look at the last problem. I didn't have a chance to finish this with my other class, so I'm going to get through this, and then I'm going to post this video up instead of my other class video. So here we have two blocks of mass m and 2m right here, right? Where m is equal to 2 kilograms. So this one is 2 kilograms, and this one is 4 kilograms. Right? The spring constant K, this K value right here, is equal to 200 newtons per meter. That has one end fixed, right, as shown here in the horizontal surface, and pulleys are frictionless, right? This pulleys, and the pulley is massless, so you don't have to worry about the rotational, right, moment of inertia. And the system is released from rest with spring unstretched. So it starts from equilibrium position, right? And it's released. So it's going to go like down, and then the spring is going to pull it back up. So it's going to go back and forth, hopefully. Okay? So, since the table and pulley are frictionless, the work done by non-conservative force is 0. Therefore, we can use total energy initial is equal to total energy final, which makes it a lot easier. Because if there were any friction, oh my God, you know what I mean? There's going to be a lot of trouble there. All right? So we can say now, okay, total energy initial is equal to total energy final. So what's going on? Well, we have to look at both of these blocks simultaneously, okay? If we were to look at total energy initial is equal to total energy final, right? What is the combined kinetic energy of two masses after the hanging mass has fallen this much? Okay, so when this thing falls down this much, it loses potential energy gravitation, right? And gains kinetic energy, right? So at this point, right, you you lose potential energy, so potential energy loss, but kinetic energy gain, right? At the same moment, when that falls that much, this thing will actually have, right, potential energy spring gain and kinetic energy gain. But there's no potential energy gravitation for this one, right? Does that make sense? All right. Now that we know that, let's take a look at what's going on. Okay. Um, so I'm going to split them up into two different colors. So hopefully we can. I'll do this in purple and I'll do this in blue. So total energy initial. I can have kinetic energy initial plus potential energy spring initial plus potential energy gravitation initial, and I can have kinetic energy initial plus potential energy spring initial plus potential energy gravitation initial. That has to equal to kinetic energy final plus potential energy spring final plus potential energy gravitation final plus kinetic energy final plus potential energy spring final plus potential energy gravitation final. We're going to consider this to be our zero right here if you want. Does that make sense? All right. So the height that it originally possesses happens to be 0.090 meters. So let's think about all those things that we possess at the beginning. Do we have kinetic energy for this block when we release it from rest? No. Do we have any potential energy of spring when it's released? It was released when it's unstretched or uncompressed, right? Unstretched. So, no. Does this thing have potential energy in gravitation initial? In a sense, yes, because it does have height from here to here. But does it change here? The height doesn't change for the blue block. Does that make sense? Therefore, this is zero as well as this is zero. I mean, you could think of it that way. What about kinetic energy for this one? Does it have kinetic energy when it's released? No. Does it have any potential energy of spring on this thing? No. Potential energy gravitation? Yes, this remains. Kinetic energy final? Yes or no for the purple block? When it's down here, it has to be moving. This has to be moving when it's going down. It's not going all. This doesn't mean it's going to stop here and it's going to go back up. It's actually, it could be even going further down. So it's definitely in motion. So this stays. Right? This definitely stays. What about potential energy of spring final? Do we have potential energy spring final? It definitely has potential energy spring final. Okay? Because, well, if I were to look at this by itself, we already have potential energy spring. But this is not attached to a spring. Only this is. Okay? So what's going on with this? No. Do we have potential energy gravitation final for the purple block? No, because we consider this to be our zero, so we have no potential energy gravitation. So the only thing that's remaining are just these. All right. So here, what do I have? I have 2mgh initial is equal to, right? Here, this kinetic energy and this kinetic energy, I have two kinetic energies. I have 1/2 mv squared. This v and this v has to be the same because they're attached to each other. Does that make sense? Right? Plus 1/2 2m v squared. Right? Plus potential energy of spring, 1/2 kx squared. X final. This x final, how much will it be stretched? We know how much it stretches. Come on, think it through. There you go. Because it falls this much, so it has to stretch same amount, right? So x final has to be same value as 0.090 meters. All right? So now it's all plug and chug, really. All right, so let's do this. So we're looking for combined kinetic energy of two mass. Oh, so we're looking for these two combined kinetic energies combined together. So we're not going to even plug anything in. We're just going to bring this to the other side and solve for this whole kinetic energy right here. We're looking for combined kinetic energy of the both masses. So this combined kinetic energy now is equal to, right, basically 2 mgh initial minus 1/2 kx final squared. So here, right, we have 2 times 2 times 9.8 times 0.090 minus 1/2 times 200 times 0.090 squared is equal to the total kinetic energy final, or total kinetic energy basically. All right. So if you do it, what do you get? I guess you get something like 3.528 minus 0.81 is equal to the total combined kinetic energy. and that comes out to 2.72 joules. So that was part A. What about part B? Well, part B, it says, what is the kinetic energy of the hanging mass after it has fallen that much? You should be able to calculate that out, right? Is that good? I'll post the rest of the solution up on the Schoology. Okay. All right. Have a nice day, everyone.